So, welcome again to the GeNoCAS non-commutative geometry seminar. Our speaker today is Franz Luef, and his title, you can see it there, Linear Deformations of Heisenberg Modules and Gabor Frames. Please, Franz, go ahead.
Thank you, and thank you for the invitation to present my work in your seminar. So this is joint work with a former postdoc, Malte Gerhold, and a former PhD student, Arvin Lamando. And it's based on this way to view Heisenberg modules over noncommutative tori in terms of so-called Gabor frames. And about 20 years ago, Feichtinger and Kaiblinger proved some interesting results about Gabor frames, which they called linear deformations. And so it was somehow natural to try to extend these results to this Heisenberg modules setting, but this turns out to be quite technical, and we had to rely on techniques from L bundles and this Banach bundles and sister bundles over, in our case, some locally compact space. And the nice thing is, it turned out that using this kind of setup, it allowed us to extend the original results by Feichtinger and Kaiblinger to this framework of Heisenberg modules, and also obtain what's called a Balian-Low type theorem, which has not been so much studied in the Heisenberg module setting, but is an interesting no-go theorem. So when you cannot have like generators, so we'll spend quite some time on like the basics, the Heisenberg module setting and Gabor frames, and what I mean by linear deformations, but to make the motivation why we want to actually do this bundle construction in the end. And it's really also an interplay between methods from like results from Feichtinger and Kaiblinger on one hand, or like stuff from Riefel on the other hand, and my students and myself. Good. So just to set notation, we're going to be interested in this noncommutative torus, which is generated by a real symmetric matrix theta. And so we are given some unitaries u1 to un, and we say that they have to satisfy this commutation relation. So if you commute two of these unitaries, then you pick up a phase vector depending on this matrix entry theta ij. And for us, it's going to be important that we can always realize, we can realize them as some twisted group C algebra. Okay, of course, there's a typo. So we're going to assume that theta is invertible, which then implies that n has to be even, because we have this symmetric matrix which has vanishing determinant for odd dimensions. And so this is somehow my take on Riefel's construction of Heisenberg modules from 1988. So, and that's also the motivation why I called them Heisenberg modules, because the Schrödinger representation is one of the standard representations of the Heisenberg group. So we are taking a point set which depends on x and omega in phase space R2D, and we define this Schrödinger representation pi of z g of t by translating g and then multiplying it with a phase vector. And elementary computation going back to the early days of quantum mechanics, whatever, shows that the product. So that's not a unitary representation on the nose, but it's one where if you look at the product, you pick up a phase factor when you add the points z and z prime. And so nowadays we call this C2 cocycle in this particular form. And so in other words, we have this projective representation of phase space. And which also then implies that we have very specific commutation relations for this representation pi of z. Sometimes I'm going to call this pi of z's time frequency shifts for the obvious reason, because it's this translation, and this modulation, because this modulation on the frequency side is a frequency shift. Yes.
Yeah, sorry to interrupt you.
Please.
Yeah, so you are referring a representation of R2D?
Yes.
In where? In L2?
On L2 of RD. Oh, I didn't. Yeah. Okay. Sorry.
Oh, so Z is in L2 of RD.
G is in L2 of RD. Yeah.
Okay.
Yes.
Okay, so you translate and then multiply. Okay.
Yes, exactly.
And it's projective?
Yes, because we have this cocycle that comes up.
Okay.
Because if you I mean, you have this translation and you have this modulation, which these are the Weil operators. And this is Weil's form of the canonical commutation relations. And if you want to interchange them, then you pick up exactly this phase factor. So here you have a modulation, a translation, and a modulation and translation. So if you interchange this translation with a modulation, then you pick up this phase factor. And if you do this commutation relation business, then you do it twice. And that's why you end up with this symplectic form associated to these 2 points, z and z prime. So this is the so-called standard symplectic form on R2D, and it's induced by the standard symplectic matrix J, defined in this way. And there's other ways of defining it, but I will stick to this one. And please, interrupt me anytime if there's anything that's not clear. Good. So this is the standard. This is going to be our setup. So this is going to be the representation that I'm interested in, and that's the one that we're going to use to realize our noncommutative and then also construct the Heisenberg modules. So the key thing is that, by linear algebra, practically, I mean, you have to do this for this skew-symmetric form induced by J, but this skew-symmetric matrix can be written as LJ L transpose for an invertible matrix L. This is like what's called the linear Gabor theorem. But there's a nonlinear form that says that any symplectic form can be written in local coordinates like this. So this is like the baby version that you can do by hand. And so in this way, we always can associate to such a theta an L. And I can type. Where if we use this setting, then our theta ij's become this symplectic. So you take the standard basis vectors, you look at L of E ij, and then you compute what's going on, and then you see that the symplectic form becomes this symplectic form of the column vectors of this lattice, of this generating lattice matrix. And so if you then use this unitaries where you look at this Schrödinger representation of Li and Lij, then this exactly satisfies the commutation relations that we want. So now this is this way of looking at. So this then leads us to, because of this co-cycle condition, that A theta is the same as this twisted group C star algebra of this lattice LZ2D with this co-cycle C, where this L really is the one that satisfies this, so gives us a way to write theta as LJ L transpose. Or you can also think of it as like you take all this LKs, where K runs over all points in the integer lattice, and you look at the corresponding operators, and then you take the norm closure. And so there is this little ambiguity that there is not a unique choice of L that you can use for writing this theta. You can use, if you have like two matrices that satisfies as L and L prime, that diagonalize our theta, then this is precisely happening if you move over DL when what's called this matrix L prime L inverse is symplectic, which is this condition as J as transpose equals to J, which comes out if you want to look at for those operators, as for those mappings on phase space that preserve this standard symplectic form, because you can write it as if you have this description in this way, and then you look for those matrices that satisfy this, preserve this symmetric bilinear form, and that's exactly the condition. But it's we are not going to care about this ambiguity. It's not going to be relevant for us. We're just pointing out that there is different choices of L that give rise to the same theta. Good. So here I'm going to deviate from Riefel's construction. So in order to construct these Heisenberg modules, we're going to, one uses a nice class of functions, which is like invariant under this representation, and has some other nice properties. And Riefel used the Schwarz space, which, is of course fine, but here I want to use a Banach space, this space, what's called Feichtinger's algebra M1 of RD. And it's defined in terms of the matrix coefficients of the representation. So we impose that this matrix coefficients are integrable for a fixed nice function G. So let's say a Gaussian, but you can also take any other Schwarz function, and you get an equivalent norm. So it looks like on the a priori that the definition of this space depends on the G, but again, using some basic representation theory, you can show that that it does not depend on G, and so you're actually free to choose whatever you want. And of course, a very common choice is the Gaussian, but you could also take any other Hermite function, or whatever you find useful. But the key thing is that this is a very nice Banach space, which shares most of the properties of the Schwarz clause, except for this differentiability conditions. But like it's invariant under the Fourier transform. It's invariant under the Schrödinger representation. So as I said before, this pi of ZF for an f in M1 is going to be again in M1. Oh, I did not define VGF. Okay, VGF is exactly this inner product f pi of ZG. This what's called this is matrix coefficient, and this is shorthand for this. And so if we have two functions in this Feichtinger algebra, then also this matrix coefficient is again in M1. It's not just an L1 function, it's in this space M1, which consists of continuous functions vanishing at infinity, and they're actually even nicer than this.
Sorry, the matrix coefficient that
Hmm?
depends on the z variable or not? Or you mean for every z? Or
This holds for every set.
No, in the Vg of f, right? Vg of
Yes.
f is a function of z.
Yeah. So
So that's the function of z that is in M1.
yes.
Okay.
So I do it on the yeah. I do it on the phase space. So this is now a function on phase space. So I do this corresponding thing for the phase space, the corresponding Schrödinger representation. I didn't want to write all this down, but
Okay. Just trying to.
so it is a function on phase space, and then we take the short-term Fourier transform of this, which is so you take the analog for the double phase space, and then you compute it, and then you see that you can split the integral and do Fubini, and then you get that straightforward. But there's actually a deeper property behind it. So actually we have the projective tensor product of M1 with M1 is isomorphic to this M1 of the phase space. So and also the fun thing this thing and the next thing are going to be important for our construction, because if you take this pi along all these lattice points, and you look at this time frequency shifted versions of G. So it acts on your G, and then you take an L1 linear combinations of these, and then this is still in M1. So you can estimate, have this estimated the M1 norm of this linear combination is still in M1, and it's bounded by the L1 of A of the sequence A and the M1 of G. And there's many other properties that, I mean, you can do periodization, and you can restriction to subgroups, and so practically all the things that you want to do in harmonic analysis are fine. So you can also do Poisson summation without thinking. It's also fine. Yeah, there's tons of other things you can do with it. So it also has a kernel theorem. So if you look at mappings from M1 to its dual space, then these in a continuous mapping, linear mappings, then they have a kernel again in M1 and so on. So there's an analog of Schwarz's kernel theorem, which also works here. So which has been used a lot. Good. So there's also naturally weighted versions of this space. So you, instead of an L1 condition, you do a weighted L1, where you take this standard radial symmetric weight, 1 plus z squared to the S1 to the S over 2, and impose this as your integrability condition. And then one can show that now the intersection of these M1 spaces with S greater or equal to 0 really become always like get nicer functions with more and more regularity. And so in the end, you really get this class, Schwarz's class of test functions, and its dual space is the space of temporal distribution. And so the advantage of this is like that you have like a non-local characterization of the Schwarz class. Like, I mean, this is like only using this representation of the Schrödinger representation and some decay condition of this matrix coefficients. Okay. So many of the results that I'm going to present, which I'm not going to present for like Riefel setting or Kohn setting for the Schwarz class, can be deduced from the results that I have by just taking these weighted versions and then take intersections. So there is these actions, that the action, so there's a nice action when we restrict. So we have this twisted group C star algebra, and inside of it sits this twisted group algebra. So if we take now, so this is the main reason for using this Feichtinger algebra, because it fits very nicely. It pairs very nicely with the twisted group algebra structure. So if we take sequence in L1, then as we've seen before, that then this mapping A to this linear combination of time frequency shifted versions of G over the lattice gives you again an M1 function. And if you take F, then you get so F and G in M1, then we've seen that the continuous version of this is in M1, and then you can restrict it to the lattice, and then it turns out this is an L1 sequence. So in other words, we can make sense of these of this inner product FGL, the C star valued, which is in turn actually then just the twisted group C star algebra L1, and those are this action A by this sequence as by this operator AK pi of LK on G is again an M1 function. So we can complete now. You can show it's a full left table C star module, and then you just take the completion with respect to this norm, and then we get this Heisenberg module over this twisted group C star algebra. And then if we have an L that satisfies L, J, L transpose, then we have this noncomputative description.
So sorry,
yes.
In the first line, when you define the two mappings, is it so the one that gets mapped to the sum, isn't it G instead of A? Because there is no way on,
or the A.
Or are you defining a map?
The A is this mapping A as this operator is sum of AK pi L of K, this operator A in the twisted group.
So it's a mapping defined on L1.
Yeah, we first defined on L1, but this is dense, so. So it's this pre-module. It's this pre-module construction. So we pick this. We pick M1 as our pre-module, and we pick a nice subalgebra of the algebra of the C star algebra, and define everything there, and then complete it. You have to work. You have to check all these conditions in Rieffel's construction. But this is like in his Schwarzkopf case.
Okay.
And you can do the same thing for the so we call it the adjoint lattice, but people also call it the dual lattice because it's the dual lattice for the, if you want to do Poisson summation for the symplectic Fourier transform, then this is like the lattice associated to it. But it's like it's all the operators pi offset that commute with the original time, also pi offsets from the lattice L that you started out with. So this is like how you get your commuting actions. It's like by picking an appropriate lattice, which we call L circle, and you turn it into a right Hilbert system module. So you have to modify your inner product accordingly. So you interchange this, and then you also do a star here in the conjugation. But and then you complete it again, and then you get the corresponding right system module. And the key thing is that there's an L missing. So this is FGL acting on H. So this rank 1 operator over this original module EL can be rewritten in terms of this right inner product, which, if you write it out, looks exactly like this. So it's this relation f pi l kg pi l kg. Good. In other words, so and the key thing about these Heisenberg modules are that they are finally generated for any invertible matrix L. So for any lattice of R2D, so of full rank. So in other words, there exist generators G1 to Gn, such that any f in the module can be written in this form. And so this finite as a sum of finite rank operators. And since this twisted L1 of this lattice is actually spectrally invariant in this twisted group C algebra, then you get that you can actually pick the windows as the generators in this Feichtinger algebra. And so every f in the Feichtinger algebra has this description. And good. So now we're going to rewrite this in a nice way. Or before this, I want to say that there's a canonical trace on this C star algebra. So for the twisted L1 algebra, you can define it this way by picking up this Serif component as a Serif Fourier coefficient, and then you extend it by continuity. And there is this interesting thing that the structure, so the behavior of these modules somehow depends on if the noncommutative torus is generated by a rational or non-rational theta. So if one of these theta ij's, so these entries of this theta matrix, are it's not rational, then we call it a non-rational noncommutative torus. And if all of them are rational, then we call it a rational noncommutative torus. And the key thing is that, I mean, the non-rational case behaves much better. It's much better behaved than the rational case, and also much better understood. So, for example, thanks to Rief, we know that like the positive cone of K0, exactly those elements on which the trace is strictly positive. And that if we have that two projective modules represent the same element in K0, then they are isomorphic, which is equivalent to this, that these projective modules satisfy cancellation. And exactly this is like what breaks down in the rational case, like for n greater or equal to 4 or 5. So, and also he also showed that practically, these Heisenberg modules are practically all the projective modules that you have up to tensoring them with some free modules or some. So it's really, if you understand this Heisenberg modules, then you have actually understood all the projective modules or this non-commutative. But that's not the case for the rational situation. So, so there is this way of linking this Heisenberg modules with these Gabor frames, which grew out of the work of Dobishi, Yves Meyer, and Alex Grossman from the 80s. They did this in the two-dimensional case, but so it's also was at the same time when they did this wavelet stuff. I mean, at the beginning they were doing this in parallel, doing this Gabor systems and also this wavelet systems, and so you pick your lattice L set to D, and you, as we say, you pick all the time frequency shifted versions of an L2 function, and this is in general an overcomplete system, and it's of course not clear, and it's also not independent. So it's a priori not clear how to define when these are nice systems. So the first who studied this kind of systems was Dennis Gabor in 46, where he picked the Gaussian and for L the standard matrix as a the identity matrix. So he looked at the integer lattice, and he tried to somehow convince people that this is like a nice system. But the problem is that yeah, it is as I would say C layer. It has this yeah, it is not a Gabor frame, and that's why it doesn't have nice properties that he actually wanted to or anticipated it has. So somehow we need some kind of stability. So this should be a KL, LK. So we take all this matrix coefficients, we look at the modulus squared and sum this up over the lattice. And then we want that this is somehow an equivalent norm to the L2 norm. So we again copy paste. And sometimes we cannot use just one window, then we have to use finitely many, so then we call it a multi-window thing. And so if we so natural class of operators that you can associate to such a system are these what's called mixed type systems. So you one says that you analyze your f by using this system pi lk with g, and then you rebuild, also synthesize it with a system that's generated by another function h. And yeah, in the case where g is equal to h, we say that this is a Gabor frame operator. In the other case, it's called a mixed type Gabor frame operator associated to the system. And some further terminology, so if A is equal to B, then we call it tight, because then this condition here is an equality as a A times, and then the frame operator is just like A times the identity. And if this is equal to 1, then it really resembles the possible relation, and so then people call it possible frames. And these objects really are useful in a variety of situations, like audio engineering and wireless communication, machine learning, pseudo differential operators, and other areas. Because it's like it really, if you notice continuous resolution from quantum mechanics, that's like the continuous version, and this is like the discretized version. So if you do applications, then you always have to discretize, and that's where these guys come up. And also that's why Gabor used it. I mean, he said it's nice what people have been doing, but the continuous version is not good enough for applications. Good. And the nice thing is, and this is like one reason why you care about this frame business, is that you always can write down reconstruction formulas, although that the original system is overcomplete and not linearly independent. There's always like a canonical choice. So this S here is not this frame operator associated to this system. And this frame condition, slower bound A, guarantees that this operator is invertible. So this makes sense. And you can also show that this operator that you have, this frame operator, commutes with this system pi of LK, this operators. So you can actually interchange this S inverse with this. And that's why you get this very nice so-called canonical dual system that has the same structure as the original system. So it's again generated by this system pi over all the lattice points. And then you can now write every f in this form. And something that yeah, Feichtinger has realized when you study this space M1 is that you can actually have this condition not just in the L2. So this is like now an L2 condition. So this converges for any L2 function f. But if you look at this for any f in this Feichtinger algebra, then it actually also converges in this Feichtinger algebra norm. And moreover, this was a result of Gorechnik and Leiner that this canonical dual element as inverse G is again in M1 if G is in M1. So this is like one reason why you really care about these M1 spaces, because it's somehow the natural class of spaces that allow you reconstruction formulas that have more better control than just the L2 condition. And it turns out that we have this continuous L1 condition. It can be discretized, and so you can check if F is in this Feichtinger algebra precisely when this coefficients F pi of LKJ, this sampled matrix coefficients are in L1. And so yeah, as I said, you can get then this reconstruction formula in this more sensitive norm M1. And of course, as you might imagine, there you can put here like a P, and then there's actually a whole family of spaces, not just M1. There's a whole family of modulation spaces, MP, that satisfy the same thing, where you can discretize them, and the P power of this coefficients here determines if they are in the corresponding modulation space. And good. So what's the relation between the Heisenberg module stuff and the Gabor frame stuff? So if you look at the rank 1 operators, then they are exactly these mixed type Gabor frame operators. So this associativity condition has also been noted in this setting by Janssen, and then independently by Dobischi and others, and Ranshen, and then in the form that it's written here, it's due to Feichtinger and Kotzek. And the key thing is like that these generators of VL are exactly these multi-window Gabor frame operators, because it really ends up like having that you get this kind of reconstruction formulas. And one can show that you can construct these projections in A theta is exactly the same as constructing these Gabor frames, because you can take this inverse square roots, and then you get this way of constructing projections. So it's like in some sense, and there's also one thing that has been noticed. It's like somehow quite difficult to classify for a given G or for a given L, for a given matrix, for a given lattice when you get Gabor frames. And one reason is that it boils down to constructing projections in noncommutative tori and in higher dimensions, and this is hard. And if you have this frame condition only as only the upper bound, then it's a Bessel. Then we call it a Bessel system. And it was noted by Austin and Enstad that there's a natural, or there's like another way of writing down this matrix as this norm condition for the Heisenberg module, namely as it's the least Bessel bound, the square root of the Bessel bound for such a Gabor system. And this somehow also gives that one finally has that this Heisenberg module is actually a space of functions, namely this Bessel vectors with this particular property. And so it's a nice subspace of L2. So it's actually a space of functions, which a priori might not be the case, because you do this completion of your space of test functions, and then you don't know what you get. And they also noted that this associative condition holds in what we call the Jans representation. Okay, good. Now we get to the deformation part. And this goes back to something from 2004 by Feichtinger and Kaiblinger, where they noticed that you can perturb your such a Gabor frame, which is a priori not clear, because so people had like some kind of perturbation results for such systems, but they were only always in terms of this function g, but they were not able to do it for like the lattice because it's very sensitive. It's like and in particular, for example, if you would like to have this for L2 functions that you started out with your definition, then this is not true. This is just right on not true. You can have like small perturbations of the original lattice, and then it even ceases to be a Bessel system. So this, yeah, dependence on like being a Gauss frame and being able to perturb the lattice is non-trivial. And still, it's still not completely understood. But they were able to, I mean, they were able to use that you have a Banach space, and that you have all this nice structure coming from this Heisenberg modules business. They were able to show that if you start out with a nice Gabor system, G0, L0, yeah, this is this Gabor system that I don't know it's before a pi of L0k and G0. Then there exists an open set of functions in M1 and an open set of lattices such that if you now look at this Gabor system coming from this set U0 and from this new family of lattices, then this is again a Gabor frame for all these G's and L's. And somehow you can think of it that you deformed your L a little bit. And so you can also not expect that this holds for very large deformations of your L0. So this L has to be somehow closed, which is given by this V naught here. And but there have, yeah, so you can extend this to, so before we just used that you have translations and then you can multiply with characters. And this is something you have for locally compacted Balian group and its point drag dual. And then you replace these deformations of the lattice by automorphisms of this group G times G hat, and then you put the natural topology in it, this Franconia topology, and then you can extend these results that Feichtinger and Kaiblinger had to this kind of setting. This we did together with Franz, Jacobsen, and Umland. And people have also studied like non-linear deformations of this original system. This was done by Grechnik, Ortega-Siada, and Romero. And also you can do it for irregular point sets. So this is like one advantage of this setup of Gabor frames, that it doesn't have to have this lattice structure. It can be, the point set can be more general, but then of course you lose this algebraic structure, then you use this Heisenberg module situation and this noncommutative tori. Okay, and so this was the starting point. Like, is there a way to phrase this statement in terms of Heisenberg modules and noncommutative tori? Yeah, so that's the second part. So in other words, so we vary the L, which we know also means that we vary the theta, and then of course we end up with a with different noncommutative tori, and so we have to make sense of this. And then, I mean, of course, you look for some kind of continuous field situation, and then you realize, okay, that you can define like that you get like a C-star bundle over this space of schizometric matrices that determine your noncommutative tori. And so then you hope that you can show that your associated Heisenberg modules give you a nice bundle. And here's some notation. It is like the standard definitions about bundles. So we have this triple B rho X, where rho denotes this continuous rejection from a Hausdorff space to this Hausdorff space X. So X is the space, B is the bundle space or total space, and rho is this bundle projection map. And rho inverse X is is noted by px, which is the fiber over x. And yeah, we also define the sections as always. And yeah, if S is in this image of gamma, this section, then we call it, then we say that gamma passes through this point S. And we're of course interested when we have like enough continuous sections. Yeah, this is just again the corresponding definitions for Banach bundles and sister bundles. So of course there is none as conditions on continuity conditions that we have to impose coming from these corresponding norms. And so this is going to be the hard part to check continuity for the bundles that we're interested in. And of course the nice sections, so the space of sections that vanish at infinity, we are going to denote by gamma naught of rho, and this is subspace of the space of continuous sections. And we can have this precisely when this norm gamma of x vanishes at infinity. You also have it's a nice Banach space, and if we have a C-star algebra, then also the corresponding thing is a C-star algebra. Good. This is again just setting this whole thing up, and so there's this basic result by Fell, how to construct this kind of bundles in this Banach space setting. So again, the key thing is you have to have this continuity condition of the norm and a density condition of this, like approximating sections. And then you can define a nice topology in it. Yeah, this is again classic result just for the sake of completeness. And this is going to be the one, as it is kind of this finding this gamma naught inside this gamma zero, just approximating sections that allow us to construct the corresponding bundles in our case. Good. Okay. So before we start, so as I said, if we vary the lattice, we vary this theta, this skew-symmetric matrix, and also corresponding knockoff tori. And this has been done in the continuous setting using Otto Adam and Takerup. They studied like representations of the canonical commutation relations, and they're looking for like what kind of continuity conditions you can have. Like, can you have like Lipschitz continuity or things like this? They were able to, yeah, construct some families of unitary groups of operators as U and V, depending on theta and 0, 1, where it satisfies this Wiles form of the canonical commutation relations, where these if you varied the theta, you could guarantee very good guarantee held upon half continuity, and this is optimal. And then, so this was in the two-dimensional situation, and then in 2018, Gabor showed that you can have this for arbitrary dimensions by some tensor argument, and he also did it for the knockoff tori. So he obtained results for knockoff tori as well. So here it's like the continuous version, and not like restricted to some lattice and phase space. But he did this as well, and if you combine this with some results by Gerhold and Shalit, then you also get some control over this constant. So this constant can be chosen like to be 2 times square root of pi, and this somehow is optimal. And so in our framework, so let's denote our representation of this number of tori by pi theta, and then we get this kind of Hölder 1/2 continuity for these representations, which in the setting of lattices becomes this, where this pi L over line pi denotes the integrated representation of the knockoff torus. And then you get this Hölder 1/2 condition, which is the key thing that we need and to make this whole bundle thing work, to get this continuity conditions of the norms. So so using this, you can set up as you would think you would do it. You say, so instead of a theta, now I emphasize the L, which represents the theta, this L, J, L transpose. So we take all these ALs for all these lattices, and then we have this natural bundle projection map, which says that if you're having this L, then you should be exactly in this knockoff torus. And again, this another thing that we use all the time is like that we have this twisted L1 algebra sits inside AL. Good, and so we can define it, also get this continuous bundle of knockoff tori or twisted Kubse algebras. And in the same way, we can get the corresponding Heisenberg modules. And again, here it was, I mean, technically much easier to just do it for the Banach space situation. Although I don't want to touch this for the Fouché situation. So here at least we can use that again. This modulation spaces and even the weighted ones where it's used as weight. They all sit in this Heisenberg modules. So this independent of whatever lattice you have. So they sit in all the Heisenberg modules. So it doesn't depend on the L. And so this somehow gives us this nice space of local approximating sections that allow us to define the corresponding, also gives a nice constant section, which is approximating, and allows us to define the corresponding bundles of Heisenberg modules. And this somehow is like, one of the main results. Also, this is like, one of the results that Feichtinger and Kaiblinger used for the M0, also for the M1 case, we can now do for the Heisenberg module case. And so we can like approximate anything in F0. Also this our sections by something nice in M1. And the main reason is because we have this nice control of the norm of the Heisenberg module norm in terms of the M1 norm, where this G is the thing that you use to define the norm. But this is independent of the G, so it's just a constant. And so that we, in some sense, this bundle that we construct of Heisenberg modules should locally look like things that can be nicely approximated by things from the Feichtinger algebra. And so, doesn't matter. It's not so important. So now you just define fiber-wise the corresponding C-star modules as like before, and then you get the corresponding C-star as its Heisenberg module for this continuous fields. And you do the same thing as before. I mean, we use all the time that we have this nice correspondence as a relation between L1 and M1. And so everything that we did before translates into the setting of bundles. And so you get like a nice full Hilbert left gamma naught rho module. And yeah, and you can do the same thing for the right module structure, and then you can show that fiber-wise it satisfies this imperative bimodule construction, so it is an imperative bimodule. And so one of the things that again we could extend from the original construction from Feichtinger's algebra to this y-i's is that if they like these elements of the Heisenberg modules, this can form now a dual pair, so like that you have reconstruction, then this map is continuous at the point that you started out with L0. So this is like one of the results, also the key results in Feichtinger and Kaiblinger's paper is like that they say that makes their results actually work is that they can deform continuously the generators that they started out with to nearby lattices and still get generators or like approximate generators. And that's the show is sufficient for getting then the Gabor frame situation. And so now this is like the analog of the results that we started off with now for the Heisenberg modules and not for the Feichtinger algebra. So you start out with an element in the Heisenberg module associated to L0, this lattice L0, and you say this is a frame. Then for every continuous sections that passes through this Gabor frame, you can find this nice open set of lattices that also generate a Gabor frame. And yeah, so this was not clear. I mean, it was before not clear that you could extend the results by Feichtinger and Kaiblinger beyond the Feichtinger algebra situation, because yeah, the only thing that people were aware of is like, okay, then you just take L2, but there was no nice class of like Bessel functions as a Bessel systems that behaved like the Feichtinger algebra. And this is like yeah, the formal version of this, what I said before, that you can locally deform your systems and then still get Gabor systems close by. And one thing that they noticed, what follows from this, that you can deform the original Gabor system, is that it implies that, so they had it for F and M1, so F0. So if you have a system as a lattice which has co-volume 1, so the determinant is 1, then and you have that this function is like nice enough. So they had M1, but we use this thing in the Heisenberg module. Then you can show that the corresponding system, Gabor system, cannot be a Gabor frame for L2. And this was noticed in the two-dimensional case by Balian-Low in the 80s. So they had a different version. They had like, if this is would be a Gabor frame, then for let's say set 2. So let's take the Gaussian and let's take set 2, and this had to be a Gabor frame. Then this can only happen if like this variance is of F0 and of its Fourier transform are infinite as the product of these two. So one of these two has to blow up. So somehow the system is not allowed to be very nice, so localized in phase space. If this has to be a Gabor system, a Gabor frame for something that's like set to the 2D or something similar like this. And it was not clear that you can have it for something bigger than, also what kind of classes, also what good time frequency localization means. And so one version was like now using Feichtinger and Kaiblinger, saying it has to be this L1 condition on the matrix coefficients, but it's also true for the Heisenberg module situation. Okay, that's it from my side. Thank you for your attention.
Thank you, Franz, for a very nice talk. Do we have questions from the audience?
So maybe, Franz,
Your volume is too low.
Oh, sorry. Wait. Now, do you hear me?
Yeah. Oh, yes, yes.
Okay. You mentioned that you have an imprimitivity by module between two sister algebras. Those algebras are constructed by using the lattice and the dual lattice.
Yes.
And then you have the same result at the level of bundles. You have
Yes.
a bundle of, okay. So can you show me those algebras, that the sister algebra?
So it's one is this. It's a group sister algebra generated by the lattice L set to D, and the other one is this one where you generate by this L circ, which is exactly those.
So you mean that the commutation relation to.
Yeah, exactly. Where the commutation relation is trivial. So it is exactly where this thing here is then the identity. You look for those. I know. Here. You look for those where you start with the LKs and then you look for those Z primes for which this is then the identity. I mean, it's like in the standard Fourier situation. If you look at the dual lattice, then you also look for those that where the phase vector becomes trivial.
Okay.
Yeah.
And that gives you that kind of associativity with the bimodal structure.
Exactly, because I mean this then allows you to do Poisson summation. So you take, where is it? So you take this and then you take the inner product with another function, and then you realize this is a product of two of these matrix coefficients, and then if you take the Fourier transform, then it becomes again a product of these, but you change some of these functions, and this is, I mean, it all goes back to Riefel. I mean, this is exactly what Riefel did.
Okay.
So here you realize that you need something where you can do Poisson summation because you and Fourier transforms and this stability under Schrödinger's representation, and then you get this associativity condition. Yeah.
Okay, thank you.
I have a little question. Does the fact that you have a bundle of sister algebras imply anything about those corresponding to closed fibers, or fibers that are close to each other?
I mean, the nice thing is because we have this twisted L1 algebra sitting inside of these bundles. So we have this inverse closed bundle of Banach algebras. We have this that you have locally, as that you have this that you cannot just have reconstruction formulas using functions in the module, but just also in this like M1 setting. So and that I don't know how to get that without this bundle construction. And also this has not been done classically, and also Feichtinger and Kaiblinger have not been able to do this because they don't have any kind of continuous field or whatever bundle situation because they do it by hand.
Mm-hmm. Are there any further questions?
As the main question still is like, I really would like to, I mean, so this, as I said, this construction of projections in noncommutative tori is equivalent to constructing these Gabor frames, and it has been an open question for quite some time. If you can, for any lattice, construct such an element in Feichinger's algebra that gives you a Gabor frame, so a projection is noncommutative torus, And for the case of the non-rational situation, I could use this results per refill to show that you can do it in the non-rational case. But in the rational case, there have been some results by Enster and Thiele, also Thiel and a third author, where they give some criteria for the existence in the rational situation. But again, they cannot solve it because, I mean, they use some kind of classification results. But since this non-commutative don't satisfy the nodes, they only get like some kind of criteria. And so, I mean, this is like, yeah, I mean, exactly. One hope was like to use this, to extend this results by Feichtinger and Kaiblinger and refine this deformation results to like somehow use that you know it for the non-rational case and you form it a little bit, you can still guarantee it's a generator, and then but we don't have path connectedness. I mean, we need somehow a result that guarantees that we can find a nice path between the non-rational and the rational one close by, and this is, I don't know how to get that. I mean, it's like the analog. I mean, Rödem and Hagerup have these paths that they can pick, and it would be nice, like somehow being able to use their results and like guaranteeing it for small enough theta's. But yeah, that's exactly. I mean, yeah, that was the main motivation for doing it, but we still cannot handle this.
I see. Thank you for your so do we have more questions from the audience? Otherwise, I'll stop the recording here.